Hi, James again. Today we're doing problem 5 from homework 9, and it's about Faraday's law. We're going to calculate the induced EMF in a coil at a particular time. So I write down Faraday's law, which is that the EMF is minus n d phi dt, and I'm really interested just in the magnitude of the EMF because I'm not given a diagram. I don't have to figure out which way the current's going to flow or anything like that. So I'm just going to take the absolute value of both sides. And the flux is the magnitude of the B field times the area of the coil of wire times cosine of the angle between the B field and the area vector, which is normal to the plane of the area. And it says that the B field is going to change in time. The area doesn't change in time, so I can bring the area out. And the angle doesn't change in time. The coil's not rotating or anything. And so I bring cosine theta out, and so I get dB dt. And the angle theta is 0 degrees because it says in the problem that the magnetic field is directed perpendicular to the plane of the coil, which means, recall that the direction perpendicular to the plane of the coil is the direction of the area vector, which is normal to the actual plane of the area. And so since the B field is perpendicular to the plane of the coil and the area vector is perpendicular to the plane of the coil, they're parallel to each other. So the angle theta is 0 degrees. And dB dt. Okay, and now I can plug in. So n is 35. It says a 35 turn circular coil. The area, it says there's a radius of 3 centimeters, which means that the area is a circle, and the area is going to equal pi r squared. So pi times the 3 centimeters in meters divided by 100 squared. Cosine theta is just 1. And dB dt is ddt of the expression given for the B field, which is this. And their units, I'm going to leave the units, I'll put the units at the end just to keep track of them. So 0.0100 t plus 0.04 t squared, 0.040 t squared, and times the units, which are Tesla, because it's a B field. And we're I should, okay, this isn't, forget about the units. I'll put units in at the end. The units here are, yes, so the B field overall is in Tesla. T is in seconds, which means that this 0.01 is actually in Tesla per second, so that the units come out right. This term has the units of Tesla, the units of B. So the 0.01 actually has units, which it would be nice to put them in, but I'm not going to bother. The 0.04 has units. Ask yourself what the units of the 0.04 are. If you want to pause here, go ahead. Okay, the units of the 0.04, B is in Tesla. The 0.04 has to be in Tesla per second squared, right? Because Tesla per second squared times second squared gives Tesla for the B field. So we're not being very careful about writing down units. Okay. And I'll put the units in at the end. Ask yourselves, what units should I wind up with for the final answer, right? It's an EMF. We'll see at the end. So anyway, 35 times all of this stuff. So I'll just leave that as it is, 0.0300 meters squared. And I want proper units, so I'm just gonna put in never mind. And then times 1 times ddt of this whole thing. Well, ddt of t is just 1, so I get 0.01 plus d dt of t squared is 2t, so I get 2 times 0.04 t, and so I get 35 pi 0.0300 meters squared times 0.0100 plus 2 times 0.04 times t, which is given as 5.6 seconds. All right, now I can plug that into my calculator, which I'll pause the video and do. And it comes out to be 0.045, and the units, some EMF units are volts. So it was really a pretty much a plug and chug. I mean, with some things to bear in mind, like you plug in B as given, take a derivative, and the area was constant, the angle theta was constant, and n is the number of turns of wire. So I talked at great length. Yeah, short problem, apart from my talking a lot. So thanks for listening, and I hope this was of use, and have a nice day.